Welcome to the video detailing Chapter 7's sampling distributions of the sample proportion. Let's first quickly go over the formulas and assumptions that we'll need to work a sampling distribution of the sample proportion problem. And first thing we'll do is look at those assumptions. So as you recall from the previous section, the sampling distribution of the sample mean said that if either the population is known to be normal or if the sample size is 30 or higher, that allows us to assume normality and use the standardized distribution or the Z distribution to work with. Now, the assumptions still need to be met in order to assume approximate normality, but in this case, those assumptions are going to be that both n multiplied by p, p is going to represent the sample proportion of success, n times p and n times the complement of p both must be 5 or higher. So if both of these conditions are met for a particular problem, we can assume normality and proceed with solving it using the standard normal distribution. All right, the mean of a sampling distribution of the sample proportion, just like the distribution of the sample mean, is equal to the population proportion. And standard error, which effectively is the standard deviation of the sampling distribution of the sample proportion, that standard error is equal to p multiplied by 1 minus p divided by n. And we'll take the square root of that to get that standard error. And finally, in standardizing a sampling distribution of the sample proportion, if we know a specific sample proportion value, then we'll run it through this formula, very similar to the sampling distribution of the sample mean. Only difference, x bar is now p hat. All right, let's take a look at a sample problem here, and we'll see if we can solve it. The Food Marketing Institute shows that 17% of two-person households spend more than $100 per week on groceries. Okay, so I see a proportion here. It sounds like this could be a success or failure type of experiment. So reading on, assume the population proportion is P equals to 17% and a simple random sample of 800 households is selected from the population. What is the probability that, so we're solving for a probability, that the sample proportion will be within plus or minus 2% of the population proportion? So let's go ahead and come up with our mean of the sampling distribution of the sample proportion. That's equal to P, which we determined was 17%. And the standard error then is going to look about like this. And finishing the math up on that, we have 1.33% for this standard error. So go ahead and sketch this distribution out. In this case, our n is 800. So the smaller of the two assumption values would be n times p. That's going to be well above 5, so both of our assumptions are met. And we'll go ahead and label our x as p hat. So start in the center here. 17% is the mean of our sampling distribution of the sample proportion. Our upper and lower specs this time are within 2%. So the value that is 2% below 17% is 15%. The value that is 2% above is 19%. So that's going to frame the area that we're solving for. And let's go ahead and convert our lower boundary over to a z-value. So the z-value of the lower boundary of 15% is equal to that p hat value minus the mu of p hat divided by the standard error value. And that is going to come out to negative 2% divided by 0.0133, which rounded to 2 decimals is equal to negative 1.50. Negative 1.50. So I'll refer to my z table once again and go to the negative side. Negative 1.50 has the area to its left of 0.0668, and knowing that, I can take advantage of the symmetric property, and because this tail area must be the same area as the left tail area, the z number will be the corresponding negation of negative 1.50. So let's go ahead and finish this part of the problem up. So here I'm saying that the probability that a randomly selected sample proportion from a sample of size 800 will be equal to the whole 100% minus 2 of the tail area that we found, and that's going to solve out to 1 minus 13.36%, or 8664. Okay, good work. Hope that's making sense. Let's move right on down to problem B. What is the probability of that? So again, we're solving for a probability. Sample proportion will be within 2% of the population. So thus far the same scenario as in part A. Of when a sample size of 1600 is selected. So that's going to be what changes here. Part A, we had a sample size of 800. We're now going to increase that to size 1600. So let's see what happens there. And what I'm going to do is just draw half of a normal distribution out here just to further illustrate how the symmetry principle helps us out. So the axis here that we're going to be solving for is, or that we're starting with, is p hat. We'll find the corresponding probability, and our lower p hat boundary, still 2% below 17%, 15%. And why don't we go ahead and we're going to recalculate that standard error value now that the sample size has changed. So numerator stays the same, 1600 down here. So now we have a standard error of 9.4%. Excuse me, 0.094%, just below 1%. So notice that increasing the sample size has decreased our standard error, or brought the elements closer to the center of that sampling distribution. So next thing we're going to do is find the z-value corresponding to our lower sample proportion boundary. That is 15%. So I'll use my p hat to z conversion formula. 15% minus 17% divided by standard error that we calculated here, and that's going to give us negative 2% divided by 0.0094, or negative 2.13 for our z-value of interest. So notice that our z-value with the larger sample size, 2.13, is now farther out the distribution than was this one, part A. Here we were 1.5 standard errors or standard deviations away from the mean, but here, by increasing that sample size, we've now effectively moved some of this tail area into the shaded area in the middle. So let's find the area corresponding to z of negative 2.13. Head right to our z table. Negative side, negative 2.13, has an area of 0.0166 to its left. 0.166. So almost have this problem done. We'll go ahead and write this out. So start with the whole 100%. We want to get rid of those two tail areas, each of which we know has this much area. So we'll simplify that, solve it, and we're going to come up with 96.68%. So again, contrasting this finding with part A, the sample size in part A, 800, gave us a percentage of the population of 86.64% falling within that range. And in part B, increasing sample size raised that 86 by approximately 10%, and now 96% of all possible sample proportions of size 1600 fall within the boundaries. Alright, good work. Let's move to part C and finish up this exercise. Part C asks us within what range. So when I see that, I'm thinking a lower and upper p-hat boundary value should the middle 95% of the sample variations fall. So let's go ahead and sketch this out so we have a good intuitive sense of what we're working with. So middle 95%. So our 95% interval is going to be symmetric to the curve because 95% is in the middle. That implies that half of the remaining area, so half of the remaining 5%, must be in our left tail, and the other half of the remaining 5% must be in our right tail. Okay, let's go ahead and put a z number onto this lower boundary. So the z number that has an area of 0.0250 to its left is, and this is the most common z-value that you're going to encounter, so soon you'll know this one right off the bat. So a tail area of 2.5% corresponds to a z-value of, on the left side of for the left tail, negative 1.96, and correspondingly the right side of the tail, the symmetric z-value, positive 1.96. So almost got this one solved. We'll check our sample size here. In this case, part C is 1600. That is the same sample size as part B, so we can just copy the standard error that we computed from part B, and it will remain the same. So all that is left is to set up our equation to convert from z-value to p-hat. So p-hat is equal to the mean value, 17%, plus for the lower boundary, we have a z-value of negative 1.96. And what that says is that the value that we want is exactly 1.96 standard error values below this mean value. So I'm going to go ahead and rewrite this just a little bit. We'll save a little bit of writing steps here, and hopefully give you a little bit more insight in this. So what I'm going to do is just migrate this negative outside of the parentheses. So rather than writing this separately as 17% plus positive 1.96 times the standard error, I'm going to write both of those together as 17% plus or minus 1.96 times 0.094. And in doing the math on that, 17% plus or minus 0.0184. So final answer for this one, 17% minus this amount is 15.16%. 17% plus this amount is 18.84%. All right, hope these are all going well for you, and thanks for watching this Chapter 7 series.